Hello, everybody. I think this particular subject, when it comes to p-threads or threads in general, and copying a process, making a copy of it, which is called forking in Linux, this whole process requires a little bit more in-depth video, because when you do a fork, you don't get copies of your other threads besides the thread that's called fork, and but at the same time, you also get copies of your data, which can contain locks that have been locked. And so what happens is that you can have a copy of the process which has locked locks, which cannot be unlocked because there's no copy of the other threads that have been running. So we have to be really careful when we do a fork. And so whenever you're using threads in a library, and you want to make the library fork proof, you have to make sure that all the locks that you have been that you're using in the library, that all these locks are locked before the fork call is executed, and then you unlock them in both child and parent. And you can also obviously reinitialize the threads if you want, but the most important thing is that you have locks in a locked state when fork is called, so that when the process is copied, you have a consistent state in the child process and in the parent process, and so you don't get any deadlocks when you try to access any kind of mutex that has been locked in the parent but then never unlocked in the child. So let's have a look at how we actually do this, because it's not really it's not obvious when you're just reading about it. It's better if you can see it in practice. So I have written this little application here that let's just have a look here. We have all the application here. So what this application does is it has two thread objects. So we create two threads, and then we have some methods in each thread which lock and unlock the mutex, and we can pause the thread, we can unpause the thread, but also once we've created these two threads from our main, we then call fork, and once we have separated the parent and the child process, we have in the parent, let's make this parent and this child, we have in the parent the two original threads that have been running because nothing has changed, but in the child we only have main, so there's only one thread. These threads are gone. They're not duplicated, because the only thing that's duplicated when you call fork is the thread that you're calling fork from. And so if for any reason any one of these threads has any kind of locks acquired when fork is called, the locks will be duplicated, so they'll be in locked state. But whenever the child then tries to call any kind of method on any one of these non-existent threads, then the child will just hang. So you will have a deadlock because you're trying to lock a mutex that's already locked, and there is no thread that can ever unlock that mutex. So the child becomes effectively disabled. And so in practice, this looks like this. So we have our thread object. This is our instance of the thread. We then have a thread function, and we have a couple of we have a few, let's just move this out so that you can see. We have a few utility functions that allow us to pause and unpause the thread. And I use conditional variables here because I want to make sure that I can pause and unpause the thread from the main thread in a predictable way. And when we then go to the main thread here, we can see the logic of the application. So we initialize both threads. We then start both threads. So initialization is basically just initializing initializing the mutexes and the conditional variables. Then we start the threads, so they start running. Let's see. Basically called pthread create. And once the thread is running, it's going to lock its main mutex. Then if it's done, it's going to just exit this while loop. So we exit the while loop. But it will also set state to running, and it will signal the conditional variable that is responsible for that state. And then it will unlock the mutex. So we can then have a function that waits until the thread has started. So wait running, which will also lock that mutex. So it will wait until the data is in consistent state, and then it will loop while the running flag is not set, and it will wait on this conditional variable. So the mutex will be unlocked, the thread will be sleeping and waiting for this conditional variable. And then once the conditional variable is set, then the mutex will be locked again by const wait, and then you check again whether it's actually whether the variable is actually set, or the flag in the data structure is actually set, because you can exit from const wait if you receive a signal. So it doesn't necessarily mean that that the flag has been set. So we have to check it again. And if it's actually set, then we unlock the mutex again, because remember, it's now locked, and then we exit this function. So we can effectively wait until the thread has started. And this is the proper way of waiting until a thread has started. And once we are running in the thread, we then lock this mutex right here, and then we sleep. So effectively we have a situation where the mutex is locked, the thread is put to sleep, and then in the main function we fork, right? So, and this almost always will just create a deadlock in the child, because now we cannot be completely sure that the mutex is locked when we do fork, but because we go to sleep after we lock the mutex, then most of the time the mutex will be actually locked. And so what we'll see is that when we call fork, the child will never exit, because it will be impossible to call this abort function, because this abort function also locks the mutex. So it tries to lock the mutex. So when we do a fork in the child process, the mutex will be locked, and in the parent it will be it will then be unlocked, obviously, in the parent, but in the child it will remain locked, because the other threads that have been created, they're not actually running. So the thread function is not running, while the data structure has been copied. So what we'll get in the child is we'll get this D1 and D2, the D1 and D2 variables, but we're not going to have this function running. So thread function will not be running. And obviously, it's the best practice is to not have any threads running when you do a fork, but because you can never know whether like if you have a library that is needs to use a thread for monitoring some condition, then obviously you cannot just you cannot force the process that uses a library to call some function to stop all the threads. You can't just rely on that. So what we can do at the very least is just make sure that we don't have any locked mutexes when we end up in the child process. And so when we run this code, we can just experiment with this code and run it a few times with different settings. We'll also try to uncomment the line that locks the mutex here, and you'll just see, just to get a feel of the results. So let's run this code. So now we have the pthread at fork enabled. So if you look at the source code here, what I have done here is I lock the mutex in @fork prepare, and then I unlock it for both the parent and the child after the fork is done. So basically, when I call pthread @fork, I pass these two handlers, or three handlers, and when I then call fork, then the glibc is going to call these handlers, and I can make sure that all the mutexes are locked. And you really have to make sure that all the mutexes are locked before fork is called, because any one mutex can create a problem in the child process because of the inconsistent state. And so if I now remove this call to pthread @fork, I will not see the same result, because the child will just hang. And another thing here, because we're trying to lock the mutex here, right? And you notice that when the program was running, it took a few iterations for the it took a few iterations for this loop to enter pause state. Or let's see. Let's just see here. So. In our parent here, before we abort the parent, we run a few iterations of the loop. Basically, what is happening is that because we have the mutex almost always locked, we are not actually able to acquire it at every single iteration. So it has to run a few iterations until there is this little time window when the mutex can actually be acquired by the parent thread. And that's why it runs for multiple iterations. But without going into too much detail, let's just try to remove this @fork call and see what happens. So if we just comment out this @fork, what will happen is that now we will have the mutex in locked state when the child process is created. So now we're waiting for child, and this is where it will just hang, because the child will never exit, because now the child is deadlocked. So what we're getting here is that we're actually coming to the end here, and in the parent process, I wait for the child process to finish using wait pid. But the child process never finishes because it's trying to call thread abort, and it's trying to lock the mutex, which is just locked in the child. It never unlocked. If we remove this, so just to show you how inconsistent things can get, and it will be very hard for you to debug it unless you know what is actually going on here. So if I make sure that the lock is not acquired before sleep, and so the thread goes to sleep but the lock is unlocked, right? So most of the time the lock will be unlocked. There will be some little time slices when the lock is locked, but most of the time it will be unlocked. And because of this, at the time when we are calling fork here, when we get to this line where it calls fork, the thread is running and it's probably now sleeping, right? So it's probably in a sleeping state, and most of the time it will be. And so the fork works out all right, but we never notice any problems because the mutex is unlocked. So in the child, we just then try to lock the mutex, we call abort, and the thread is not running, obviously, so abort works out, and then we just exit normally because we are not getting into the deadlock. And it's not easy to simulate this without the sleep function, because it's such a small time slice when the mutex is locked. So you really have to sort of time in the precise point when the mutex is locked, and then get the fork to copy the process. So it's really difficult to just to simulate the case where we're not locking the mutex before the sleep and keeping it in a locked state for a longer period of time. But this is the kind of thing you will see if you're writing multi-threaded applications and you try to copy the process. You'll get very weird behavior unless you know that no threads are copied and while your data is copied. So a good thing to keep in mind, and definitely have a look at fork to make sure that you have consistent state. I hope you learned something, and good luck with your multi-threaded programming. It's really fun and it's really important. I think multi-threaded programming should definitely be the first thing people learn when they start a new programming language, because it's so central to high performance application development. And so many mistakes can be avoided if you know multi-threaded programming, and you can write your applications in a way that accounts for the effects of multi-threaded use of your libraries and of your programs once threads are introduced into the equation, which they will always be as the application develops, because we have to make use of multiple CPUs. We have to make sure that our applications are as parallel as possible, and so it's an important very central part to programming. While a lot of people don't really understand that it is quite central, and so they try to avoid threads and they try to do things like event-driven programming, whereas under the hood it's still threads. It's just that you're trying to avoid what you don't understand, and so you never look into threads. Instead, you just use some library that already uses threads and just exposes this single-threaded event interface to you, and you're like, oh, I get this event interface, I don't have to use threads, but in reality, you're still using threads. So if you really want to learn programming at a deeper level, you should study threads and learn threads, learn how to write multi-threaded programs. Thank you for watching, and I'll see you in the next lesson.